In this lesson, we're going to cover models for population growth, specifically exponential growth and decay. This definition says exponential growth is population grows at a rate proportional to the size of the population. Our next definition is a differential equation for exponential growth. It's written as dp dt equals k times p. And next we're going to take this differential equation and we're going to solve it using the initial value p of 0 equals p naught, which is positive. So first we take the differential equation dp dt equals kp, and we're going to separate the variables. So we bring this p down to the left, we leave the dp there, then we bring dt up to the right, and so it's equal to k times dt. Next we're going to integrate both sides. Over here when you integrate this, you get ln absolute value of p. Over here we're integrating k with respect to t. So this is a constant, the integral of a constant with respect to t is going to be k times t. And then we add our arbitrary constant c. Next, we're going to plug in the initial value p of 0 equals p naught. So when t equals 0, then the population is equal to this initial population. So we're plugging in our initial population right here for p, and then we plug in 0 for t. So then k times 0 is gone, and you just have c equals ln absolute value of p naught. And up here we have that p naught is positive, so the absolute value of a positive is just itself. So that's why we have that c equals ln of p naught. Now that we found an expression for c, we take this and plug it in right here. So we have ln absolute value p equals kt plus ln of p naught. And then we have a note, because p of 0 is equal to p naught, which is positive, that means that our population, or p, is going to be positive. And if you take the absolute value of a positive expression, it's just equal to that expression. So you can drop the absolute value and you just have the natural log of p. So again, the absolute value of p is just p, so we have natural log of p equals kt plus ln of p naught. To solve for this p right here, we're going to exponentiate both sides using base e. So we write e on both sides and we raise both of these up into the exponents. So e to the ln, those undo each other and you just have p. Over here, we're going to split this, e to the kt times e to the ln of p naught. Right here, these undo each other and it drops down this p naught. And so it's this expression times just p naught, or we put the p naught in the front. And this is the solution to the differential equation. We have population with respect to time is equal to p naught times e to the kt. And then we'll use this equation to solve some of our problems in this lesson. We just have a note right here that this p naught is the initial population given at time t equals 0. So again, this is the solution to the differential equation that was given above. We have that if k is greater than 0 or if k is positive, then the quantity is increasing or grows with time. We have if k is less than 0 or k is negative, then the quantity decreases or decays with time. Then we also have the definition for half-life, the length of time required for a quantity that is decaying exponentially to be reduced by half. This example says the rate at which the population of fruit flies grows is assumed to be proportional to the number present. Suppose there are 100 fruit flies initially, and after 3 days there are 200. Part A says find an expression for the number of fruit flies in the population at time t greater or equal to 0. So I just wrote down the equation. We have p of t equals p naught e to the kt, and then I set up a little chart, a t and then p of t chart. So it says there's 100 fruit flies initially. So that means at time t equals 0, there's 100 fruit flies. So we're going to plug this in. This is our initial population right here. So now we have the equation p of t equals 100 times e to the kt. So next we use the next set of data. It says after 3 days, there's going to be 200 fruit flies. So I just wrote that here, 3 days, 200 fruit flies, and let's go ahead and plug this in over here in this equation. So we take the 200 and we plug it in for p, and then 3 is plugged in for t. So now we have an equation that we can solve for k. So first step, we're going to divide both sides by 100. So we just get 2 equals e to the 3k. To solve for k, we're going to take the natural log of both sides. On this side, we have the natural log of e to the 3k. Anytime you have an expression of this form, ln of e to a power, this is just equal to that power. So again, this just becomes 3k. And then last step, we're going to divide both sides by 3, which is the same as timesing by 1/3. So we get that k equals 1/3 natural log of 2. So now we take this expression and we're going to plug it in right here. So here we have our equation. We have 100 as our initial population, e, and then this is k times t. We're going to simplify this a little bit more. So right now in this exponent, we have 1/3 times ln of 2 times t. We're going to multiply the 1/3 and the t. So we have t over 3 times ln of 2. And by doing this, by properties of logs, because this expression is being timesed by the natural log in front, we're going to move this up into the exponent. So again, this got moved up into the exponent, so now we have e to the ln of 2 raised to the t over 3 power. And the purpose of that is now when you have the e to the ln, those undo each other and it brings this expression down. So here's our final expression for the number of fruit flies in the population at time t is greater or equal to 0. We have p of t equals 100 times 2 raised to the t over 3. Part B says, when will there be 1,000 fruit flies in the population? So I took this equation and wrote it out here, and then I made a chart. We're trying to find the time when the population is equal to 1,000. So we're going to take 1,000 and plug it in over here and solve for t. All right, so we have everything set up. So we're going to solve for t. First step, we're going to divide both sides by 100. So we get 10 equals 2 to the t over 3. And at this point, to solve for t, we can take the log of both sides or we can take the natural log of both sides. Either way will work. So I'm going to go ahead and just take the natural log of both sides. And by doing so, we can now, by properties of logs, bring this exponent and multiply it to the front. And then finally, to solve for t, we're going to multiply both sides by 3, and we're going to divide both sides by natural log of 2. So we have t equals 3 times natural log of 10 divided by natural log of 2. We're going to plug this into the calculator. So we end up getting that there's going to be 1,000 fruit flies in the population after 9.966 days. This example says, after a person drinks a cup of coffee, the amount of caffeine in the person's bloodstream is 30 parts per million. Suppose the amount of caffeine decreases or decays at a rate proportional to the amount remaining, and after 4 hours there are 14 parts per million left in the bloodstream. How many hours will pass until there are 10 parts per million left in the bloodstream? So here we have our same equation, p of t equals p naught e to the kt. And I set up our chart. We have the amount of caffeine in the person's bloodstream is 30 parts per million. So we have at time 0, we have 30. And then it says the amount of caffeine decreases or decays. So after 4 hours, there's only 14 parts per million left in the bloodstream. So we have 4 hours and then 14. So we're going to plug this in first into our equation. So I just took our initial amount and plugged it in for p naught. Next, we're going to take t equals 4 and set it equal to 14. So I plugged in 14 here and then 4 for t. We're trying to solve for k, so we're going to divide both sides by 30. So we get 7 over 15 equals e to the 4k. Now we're going to take the natural log of both sides. So over here, this is equal to 4k, and then we divide both sides by 4. So we end up getting that k is equal to 1/4 natural log of 7 over 15. So now we're going to take this and plug it in right here for k. So we have p of t equals 30 times e, and then this is raised to the k times t. Next, we're going to take the 1/4 and the t, we're going to multiply them together and put them right here. And now we're going to bring this up into the exponent. So this t over 4 gets put up into the exponent, so now you have 30e to the ln of 7/15 raised to the t over 4. And the purpose of that is because e to the ln, those undo each other, and it brings this expression down. So this is the equation that describes the amount of caffeine in a person's bloodstream after t hours. This next part of the problem says how many hours will pass until there are 10 parts per million left in the bloodstream. So what we're going to do is we're going to plug in 10 for p over here, and we're going to solve for t. To solve for t, we're going to divide both sides by 30. So next we're going to take the natural log of both sides, and then at this point we're going to bring this t over 4 down to the front. And then finally, to solve for t, we're going to times both sides by 4, and we're going to divide both sides by natural log of 7 over 15. And then we're going to plug this in the calculator. And we get 5.766 hours until there are 10 parts per million left in the bloodstream. This example says the population of a country is growing at a rate proportional to its population. If the growth rate per year is 4% of the current population, how long will it take for the population to double? Since it says that the growth rate per year is 4% of the current population, if we change this 4% to a decimal, you move the decimal right here 2 to the left, you get that k is equal to 0.04. So I just plugged in 0.04 for k into the differential equation dp dt equals k times p. So again, 4% of the current population is going to be 0.04 for our k value. And I wrote that out here. We have the differential equation in the form dp dt equals kp. We we have k is equal to 0.04, and that's positive since the population is growing with time. If the population was decreasing with time, then k would be a negative value. So what I'm going to do is I'm going to plug in 0.04 for k. So again, we have 0.04 plugged in for k. Next it says, how long will it take for the population to double? This problem never tells us what the initial population is, so we're going to leave that expression as p naught, but it's asking for the time it takes for that population to double. So that means we're going to plug in 2 times p naught, so doubling times by 2. And we're going to plug this in over here and then solve for t. So at this point, to solve for t, we're going to divide both sides by p naught. And then what will happen is the p naughts will cancel on both sides of the equation. At this point, we're going to take the natural log of both sides. And then over here, this is just going to equal 0.04t. And then finally, we just divide both sides by 0.04. So we end up getting that it's going to take 17.329 years for the population to double. This example says radium-226 decays at a rate proportional to the quantity present. Its half-life is 1,612 years. How long will it take for 1/4 of a given quantity of radium-226 to decay? So I have the equation P of t equals P naught e to the kt. Since the problem says the radium-226 has a half-life of 1,612 years, and the problem doesn't tell us how much there is initially, so that means we'll just leave this as P naught for the initial amount, but then half-life means that it's going to take 1,612 years for this initial amount to be cut in half. So that's why we just times that by 1/2. So we'll go ahead and plug this into the equation to then solve for k. So we take 1/2 p naught, we plug it in over here for p. We leave the p naught here, and then we have e to the k times and then 1,612. First step, we're going to divide both sides of the equation by p naught. So you end up getting 1/2 equals e to the 1,612k. Next, we're going to take the natural log of both sides. So then this side will just simplify to 1,612k. And then finally, we're going to divide both sides by 1,612. So here's our expression for k. So I took this expression and plugged it in for k into our equation. And we're going to do the same thing that we've been doing. I'm going to take this t and times it by this fraction. So we're going to get t over 1,612. Then we're going to move that up into the exponent so that the e and the ln will undo each other. So once you simplify that, you get p naught times 1/2 raised to the t over 1,612. Next it says, how long will it take for 1/4 of a given quantity of radium-226 to decay? So the important thing to note is it's saying that 1/4 is going to decay, so that means that you have 3/4 left. So again, P of t represents the amount present, so if a quarter decays, then you have 3/4 the initial amount that's present. So we're going to go ahead and plug this into our equation. And the first thing we're going to do is we're going to divide both sides by p naught. Next, we're going to take the natural log of both sides. And next, we'll bring this fraction and multiply it to the front. And then finally, to solve for t, we'll times both sides by 1,612, and then we'll divide this out. So we get that t is equal to 1,612 times natural log of 3/4, all divided by natural log of 1/2. So I'm going to just plug this into the calculator. So we end up getting 669.040 years for 1/4 of the radium to decay. This example says the table gives the population of the US in millions for the years 1900 to 2000. It says use the exponential model and the census figures for 1900 to 1920 to predict the population in 2000. Compare with the actual figure and try to explain the discrepancy. So in 1900, the population is 76 million. In 1920, the population is 106 million. So we're going to use this as our initial population and go ahead and plug it into our same equation. So first, I'm going to plug in 76 right here for the initial population. And next, we'll plug in 20 for t and then 106 for p. So now we have an equation that we can solve for k. So we're going to divide both sides by 76. So this fraction reduces to 53 over 38, and then over here we just have e to the 20k. Next, we're going to take the natural log of both sides. All right, and then over here this is just going to become 20k. And then finally we're going to divide both sides by 20. So here's our expression for k. Now we're going to take it and plug it into this equation right there. And at this point, we're going to move this t and multiply it to the 1 over 20, so it's going to become t over 20, and then we'll raise it up into the exponent so that the e and the ln can undo each other, and it brings that whole fraction down. So we end up getting that p of t equals 76 times 53 over 38 raised to the t over 20. So now we're going to use this exponential model to predict the population in 2000. So the first thing we want to check is from 1900 to 2000, how much time has passed, and that's going to be t equals 100 years. So we're going to plug in 100 for t into this to then solve for the population in the year 2000. So again, we're going to plug in 100 for t. So we plug in 100 right here, 100 divided by 20 is 5, and then we're going to plug this into the calculator. So we end up getting 401.121 million people. And then finally it says compare the actual figure and try to explain the discrepancy. And so we got 401 million, but from the table we have that in 2000 there's only 275 million people. And I just wrote it out that 401 million is more than 275 million because the population did not continue to grow at the same rate as it did from 1900 to 1920. This example says a bacterial culture grows with a constant relative growth rate. After 2 hours, there are 600 bacteria, and after 8 hours, the count is 75,000. Part A, find an expression for the population after t hours. So what I did is I set up our equation twice because we have the population is 600 after 2 hours, and then we have the population is 75,000 after 8 hours, and they don't give us any information about the initial condition. So we're going to plug in these values here, and then we'll plug in these values over here. So I got everything plugged in, and next we're going to isolate the p naught for both equations. So we end up getting that p naught is equal to 600 over e to the 2k, and then over here p naught is equal to 75,000 over e to the 8k. So since both of these fractions are equal to p naught, we can then set them equal to each other to then solve for k. So now we have one equation that we can solve for k. So it's a proportion, we're going to go ahead and cross multiply. So on this side we have e to the 8k divided by e to the 2k. We can simplify because they have the same base, so we'll subtract exponents and we'll get e to the 6k. And then over here on the right we end up getting 125. Next we're going to take the natural log of both sides. So at this point on the left this is going to simplify to just 6k. And then we're going to divide both sides by 6. And we get that k is equal to 1/6 natural log of 125. So at this point, we're going to take this k value and we're going to plug it into either one of these equations, it doesn't matter which one, to then solve for p naught. So I'm going to take this and plug it into this one on the left. The numbers are a little bit smaller. So we get p naught equals 600 over e to the 2 times, and then there's k. So the 2 and 6 reduce, we get 1/3. And then we're going to move this 1/3 up into the exponent. The e and the ln, they undo each other, and then we just have 125 to the 1/3 in the denominator. And the cube root of 125 is just 5. So we end up getting 120 for the initial population. So now that we have p naught and we have k, we're going to plug them into the original equation to then write an expression for p of t. All right, so we have p of t equals 120 e to the k times t. So next we're going to take the t and times it by 1/6. So we're going to have t over 6 right here. Then we're going to move up into the exponent so that e to the ln can undo each other, and then it brings down this 125 to the t over 6. All right, we're going to do one more thing. We're going to take this 125 and rewrite it as 5 to the 3rd. And then now 3 times t over 6 is going to reduce to be just t over 2. So as our final equation, we get p of t equals 120 times 5 to the t over 2. Part B says find the rate of growth after 5 hours. To find the rate of growth, that means we need to take the derivative of this function. And this function, if we focus in right here, it says 5 to the t over 2. This is of the form a to the x. And just a reminder to take the derivative of anything of the form a to the x, where this is the constant and the variables in the exponent, the formula is a to the x ln of a. So we're going to use this to be able to take the derivative of our p of t. So we have a constant, we're going to just drop down that constant. And then we have, again, this is of the form a to the x. So the derivative is going to be 5 to the t over 2 times ln of 5. And then finally, because this isn't just t, we're going to chain rule. So we need to take the derivative of this function. And the derivative of t over 2 is just 1/2. So we times by 1/2. Before we plug in 5 for t, let's go ahead and clean this up a little bit. Because this is one big product, I'm going to do 120 times 1/2, or 60. And now let's go ahead and plug in 5. And finally, we're going to plug this into the calculator. So the rate of growth after 5 hours is 5,398.219 bacteria per hour. Part C says, when will the population reach 200,000? So we have our equation and we're solving for t when the population is 200,000. So we're going to plug this in over here and then solve for t. So first step, we're going to divide both sides by 120, and this reduces to 5,000 over 3. Next, we'll take the natural log of both sides. We bring this t over 2 in front, and then we're going to times both sides by 2 and divide by natural log of 5. So to solve for t, we times both sides by 2, and then we divided out ln of 5. So you end up getting t is equal to 2 times natural log of 5,000 divided by 3, all divided by natural log of 5. I plug this into the calculator, and you get 9.219 hours. All right, guys, thanks so much for watching.